Pereira Neto, PG student from the University of Sao Paulo, and he will talk about the Blade-endwall treatment for a parameterized adjoint-based optimization of turbomachinery. The floor is yours.
Thank you very much. So my name is Murillo. I'm a doctoral candidate from University of Sao Paulo in Brazil. And today I'm going to show the work I've been developing this last year as a visiting researcher at TUDEL, mainly collaborated with Alessandro, with my supervisor in Brazil, Dr. Jurandir Anajara, and also with Matteo. So just the framework of the talk, a bit introduction of FFD and CAD-based optimization in SU2, an overview on Parablade, also a problem that we were facing when trying to do 3D optimization, a solution for the problem, and then a test case. So let's start with the basics. So we can do basically optimization using two approaches, either FFD-based or CAD-based approach. And while the first one allows us for a larger design space with more flexibility, the second one, of course, has smaller design space. We have less design variables. But there is an issue when we try to do FFD-based optimization, which are to specify constraints. So for example, if you want to make sure that our blade has a minimum thickness, it's very hard to do that with FFD-based optimization, and it's very easy to do this with CAD-based. And also, CAD-based optimization, CAD-based parametrization allows us for more interpretable design variables, so we know during the optimization which parameters are more important for our geometry to be improved. So we can then proceed with Parablade, which is the CAD code that we're going to use for in this work. And Parablade was developed, one of the guys that developed is Neto. So Parablade can carry out the parameterization of 2D blades. It's possible to define. Okay, it's possible to define as well airfoils, apply thicknesses to it. And also, if you define the geometry at different spans, you can generate 3D geometries. And a very nice feature of Parablade is the geometry matching. So if you have a mesh nodes, a set of mesh nodes, and you would like to find a CAD model, a surface CAD model that represents these data sets. So we want to find a relationship between a CAD model and also our mesh. So we want to find the best CAD model possible to represent our geometry. And here we have some examples for the Aachen turbine stator, also for the Eckert impeller. So Parablade can basically match axial geometries, radial geometries, or any kind of blade. So how Parablade, also Parablade can orchestrate the entire optimization workflow. So if we start with a design variable vector, and we have then SU2 and Parablade, just to show which part does what. We can parameterize our geometry to obtain a surface. We can deform we can use the surface to deform and obtain a volumetric mesh, run the CFD, obtain our objective function, and use adjoint capabilities to assemble our final sensitivities with respect to our design variable. We feed this to an optimizer, and we loop it until convergence is reached. So this is how Parablade can orchestrate the entire optimization workflow. And which was the problem that we were having? To show this, I'm going to get this very simple example. It's the Aachen test case. We have this reference geometry, the blue one, and the deformed one, which has a larger upper thickness. And now I'm using SU2 V5. I would like to also use the more recent versions in the future, but for now, I'm using SU2 V5. And the problem that we were having is, for instance, if we take our domain and we get a slice at, for example, 0.02 meters of axial position, something very weird happened in the intersection between the blades and the endwalls. And this kind of problem has been noticed a couple years ago, and my goal is to try to solve this issue. And why this was happening? Well, suppose we start with a baseline blade mesh. We have also our volumetric blade mesh. We have our hub and our shroud. And during an optimization step, the blade points are then moved to the orange line over there. But you can see that after the deformation, we get this blade. But you can see that at some points, the points are below the hub or all above the shroud. And this is not desired. We would like to make the blades consistent with the hub and the shroud. So a quick fix to that would be to apply the so-called tangential boundary conditions. And what happens is that you can see that near the end walls, the quality of the mesh gets quite poor. And at some points, also the mesh twists to itself and interpolates to itself. So this is the problem that we're trying to fix right now. So how to make a consistent update of Blade-endwall's mesh and geometry? Is it possible to do that? And we think so, yes. There's a solution for that using blade trim. The first thing we want to do is, if we want to respect the end walls, we have to model the end walls using a CAD. So here we have the example of the Atom turbine stator. You see that we have a revolving surface modeling it. And also we could have it for example, for the Eckert impeller, also a revolving surface to model the end. Then, something that was necessary to do was to extend a bit the blade in the spanwise direction. I'm going to show some results to show why that was the case. But this was needed, otherwise we couldn't proceed with the next steps. This is done by an algorithm of surface clamping, and we extend the V parameter from -0.1 to 1.1, so just a bit of extension below the hub and above the shroud. Yes, and this is because blade intersection may occur at points smaller than 0 or points greater than 1. Next, we had to extend the blade matching, the geometry matching procedure to match both the blades and also the end walls. So we have a consistent geometry for our test kit. So we match 3 surfaces using a quasi-Newton method proposed by a colleague of ours in our group. The next step is to calculate the blade end wall intersection. So we have a model of the blade with CAD parameters UB, VB. We have the end wall model with CAD parameters UE, VE, and we want to find the points that satisfy the intersection, which is this equation. How do we do that? We discretize UB, which is the streamwise direction from leading edge to trailing edge, and we find all the other parameters also using an optimization algorithm. Something extra that was needed. So we have all our mesh points. Every one of the mesh points was matched to an UV value. So each one of these are UV values of the mesh. And the red curve here shows the CAD calculated intersection. And you can see that at some points, the mesh does not respect the intersection. So we had to do a small adjustment to make sure that all points of the mesh now respect the intersection. Okay, so to this point, we can discuss about the trimming, which is the core of this approach. So we found UV values of our mesh. We found intersection curves that describe our geometry, our intersection between the blade and the end wall. And we would have some sort of geometry like that. This would be the trim part. We can see here the hatched regions. But since this intersection will change at each optimization step, we would have to take this into account somehow. And how to do that? We will remap all of these points to a new 0v0 space, which is a unitary square. And this will be the CAD parameters that we're going to use for our optimization. This is fixed during optimization. Yeah. This entire procedure is done once, just for the matching. And after that, we can proceed indeed to the optimization. And how to do that? Well, let's talk about the blade trim. So we had these U0, V0 points, which were obtained from the matching procedure. We have a design variable alpha k at the kth iteration of our optimization. We first have to do the step 1 over there, the end walls CAD model. We had to do the step 2, spanwise blade extension, and also step 4, the blade and wall intersection, to calculate the intersection curves. And once we calculate the intersection curves, we would obtain a curve more or less like this. And then we can map each one of the points from there to here. We would end up with a geometry more or less like this. And let's say we are now at the J optimization iteration. We will get a different intersection curve. We will then proceed again to the remapping, to the mapping of each one of the points, and then obtain again a 3D geometry. So then you can see that using fixed U0 values and changing just the design variables vector, we could obtain different geometries. And if these intersections respect the end walls, we make sure that the blade, the mesh deformation afterwards is going to respect the end walls as well. So let's go for a test case to see if this worked or not. We're going to get the same test case as before, the Aachen turbine stator, using V5. And for the DV markers at the SU2 config file, I had to specify not only the blade, but also these other surfaces, which were kept stationary for mesh deformation stability. If you want have some questions, I have some figures to show what happens if we don't specify that. But for this test case, this was necessary. And also, the hub and the shroud are informed to SU2 as marker deformed tangential. So we apply the tangential boundary conditions to them. And back once again, we have our domain. We have a few slices. And let's see what happens. Without the end wall treatment, we had that intersection problem. And with the end wall treatment, we have a better, a very nice mesh at the intersection. So the problem is not happening anymore at slice 0.20 meters. And also at other slices, you can see similar behaviors. And with that, before the end wall treatment, it wasn't even possible to run an SU2 simulation. The simulation crashed before the beginning. And with this, we could run another simulation with the deformed geometry. And we have a very nice convergence. The reference and the deformed one show similar convergence histories. And we can also see some plots of the pressure near the shroud or near the end wall. You can see some differences, mainly on the upper part of the blade, of course, which is the part that is deformed. And also the entropy generation changes a bit near the end walls. So with this approach, we could make a consistent update of blade and end walls geometry mesh. We could then solve the problem, at least for this test case. And it allowed SU2 to run CFD simulation. The future work that we're gonna do is to make a quantitative assessment of this approach, make sure that it is not something only visual, but something also quantitative that we can measure. Something that was suggested by Josh is to assess the effectiveness of this within the optimization loop, where many things are gonna change at the same time. And also, finally, I would like to apply this for a centrifugal compressor impeller, which is my main topic of my research. And I would like to acknowledge the scholarship that I received to be at NTU Delft this year and also to come here. And also would like to thank Nitish for the suggestions on the work, for Josh from the comments, Evert, and also Alessandro, who sadly could not be here. But yeah, this is what I have for today.
All right. Thank you, Murillo, for this nice presentation. Any questions, Josh? Is what I'm looking beautiful. The amount of difficulty you get with the sort of the amount of change in the design variable, but it's meant to separate down.
Yes, there is a limit to that. With this approach specifically, let me just come back a few slides. Okay, so with this approach, using the marker deformed tangential, if you deform too much the geometry, of course, at some point the mesh will become poor. But our idea would be to eliminate this deformed tangential and to include the hub and shroud also in the DV marker. But there's some work to do that. Perhaps Floyd over there could help us with that, especially regarding the mesh deformation of the end walls. But yeah, I've tested. This is an increase of 1 millimeter in thickness. I tested once increasing like 3 millimeters, and it broke, of course.
And also, comment from like a user stuff model, it was kind of like you have to specify every single marker that you have as a design variable marker. So maybe something to consider.
Yes.
Or
one thing that would be nice would be to remove, for instance, periodics, also to allow for sliding mesh. which would be something to do as well. So yeah, you're right.
Sure.
Yeah, I was wondering because I am not aware of this marker, the form conjectural option. So I'm wondering whether you ever tried with like the mesh transformation with the viewer release, viewer then it's section 5, and how that translates to that. And I would be definitely interested to get a touch with you afterwards because I made all stuff in mesh transformation.
Nice. I haven't tried with version 8. I wish I had tried it before, but to this point I haven't. But yeah, this is something that would certainly be done. Yes, for sure.
Because ultimately, we need to, and in doubt if it's still a problem, we need to get it working for version 8.
Yep.
Because for version 5, it's
Quite old. Yeah, you're right.
All right. Other question? No? If not, then thank you again, Leo.